In this video, we introduce SceneHub4D, a dataset and evaluation framework for 6 degrees of freedom 4D VR scenes. Let me first give a high-level overview. Our goal is to bring real-world dynamic scenes into VR. This typically involves 3 stages. First, we capture real-world scenes using RGB-D camera rigs. Then, we reconstruct these captures into 4D scenes, also known as free viewpoint or volumetric video. Finally, the reconstructed scenes are often streamed over the network and rendered to support 6DoF VR experiences. These types of 4D VR content enable a wide range of applications. For example, holographic live streaming, telepresence, and immersive remote interaction. Systems like Microsoft Holoportation and Google Beam demonstrate the potential of these technologies. Volumetric video or free viewpoint video enables immersive experiences such as telepresence, extended reality, and spatial computing. However, current 3D research is still limited. There is a lack of realistic and large-scale datasets, poor reproducibility across systems, and a high barrier to entry due to complex capture and reconstruction pipelines. Existing 3D, 4D open datasets have several limitations. Many of them focus primarily on human captures without explicit background geometry. As a result, they are not suitable for evaluating full scene rendering in realistic environments. So, there are datasets that attempt to capture more realistic human-object interactions, including background geometry. However, they still suffer from several important limitations in terms of capture quality and usability. For example, Panoptic uses relatively older sensor setups, which results in low resolution and sparse point clouds. Also, the data is captured in a controlled indoor dome environment, which significantly limits the diversity of scenes. On the other hand, datasets like FSVVD try to capture more realistic environments, but they often suffer from incomplete reconstruction, with noticeable holes caused by occlusions and sensor limitations. To address these limitations, we introduce SceneHub4D. Our dataset consists of long, unbounded RGB-D sequences with high-quality background geometry. It also supports multiple 3D representations, making it suitable for a wide range of research tasks. Here is a teaser video of our dataset. As you can see, our scenes capture both dynamic human motion and realistic background environments. This allows more comprehensive evaluation of 3D systems. Here is another teaser video. In this example, we demonstrate free viewpoint navigation within the reconstructed scene. SceneHub4D provides several key features. As summarized in the table, our dataset offers a more comprehensive set of capabilities compared to existing datasets. First, it includes long sequences, which are essential for compression and streaming benchmarks. Second, it captures full scenes with realistic backgrounds, enabling rich human-object interactions. Third, it supports multiple geometry representations, making it flexible for a wide range of 3D and XR research tasks. And finally, it is publicly accessible through the Open Storage Network, allowing easy use and large-scale evaluation. We analyzed the dataset using spatial and temporal metrics. Specifically, we use spatial information and volumetric temporal information to characterize scene complexity. As shown here, different scenes exhibit different properties in terms of spatial detail and temporal variation. We compare SceneHub4D with existing datasets. Our dataset covers a larger spatial volume and contains significantly more points. This is because we use modern Azure Connect sensors, which produce denser and higher quality point clouds, and we also capture complete background scenes. As a result, SceneHub4D provides richer and more complex 3D content for realistic evaluation. Next, I will explain how we generate the dataset. For the background, we use photogrammetry from around 1,000 high-resolution images, as well as laser scanning for accurate geometry. For the foreground, we capture dynamic interactions using multiple RGB-D cameras. Finally, we align the foreground and background into a unified coordinate system to construct full 4D scenes. We also propose metrics for evaluating 3D scenes. First, we define a geometric complexity score, which captures both the density and irregularity of the geometry, while also accounting for the overall scene scale. Second, we use multi-view SSIM across diverse viewpoints to measure rendering quality. Together, these metrics allow us to quantitatively evaluate both the geometric complexity and the visual fidelity of 3D scenes. Here, we show an example analysis. As we simplify the mesh, the geometric complexity decreases significantly. However, the multi-view SSIM remains relatively high, indicating that the visual quality is largely preserved. This suggests that we can reduce geometric complexity without significantly degrading visual quality. At the same time as complexity decreases, rendering speed improves, and compression significantly reduces file size. Putting these together, we observe that reducing geometric complexity can improve performance and reduce bandwidth, while maintaining acceptable visual quality. This highlights an important trade-off between geometry, rendering performance, and compression efficiency, and suggests that there is a sweet spot for optimizing 3D streaming and XR systems. Building on this, SceneHub4D enables practical system-level evaluations. It can be used to study key components such as rendering, compression, and streaming. Because the dataset is publicly available on the Open Storage Network, users can access it without requiring custom capture setups. This makes it possible to conduct reproducible and scalable experiments across different systems. Still, our work has some limitations. Our dataset does not generalize well to outdoor scenes. It has a limited capture range and uses a static setup. Also, the foreground capture relies on a fixed multi-camera configuration. As future work, we plan to integrate learning-based methods, such as depth completion and multi-view reconstruction. To conclude, we present SceneHub4D, a comprehensive dataset and evaluation framework for 6 degrees of freedom 4D VR scenes. It provides long-duration, full-scene RGB-D captures with high-quality backgrounds and multiple representations. Our goal is to enable 3D and 4D research without requiring complex hardware setups.